Okay, so I'm going to do the tutorial MFH3, which you can find in the new, sorry, in this folder here, in the version 2, because it's I did some late correction, so you should use that script. So there you will find the Jupyter Python script, and then an input to TB-Trans that I prepared that we will look at later. So this exercise tries to reproduce this paper where the authors takes two systems, an armchair nanoribbon and a zigzag nanoribbon, and perform, I think, siesta calculations and tight binding calculations and compare with different sets of parameters. And also they do calculations with the mean field Hubbard Hamiltonian, so the same as we are going to do here. And they take they try different parameters, for instance, first nearest neighbors, up to third nearest neighbors, non-orthogonal basis, orthogonal basis, and then they compare the band structures that they find, and also including and not including electron interactions. And they compare the band structures obtained with siesta and these tight binding models. Here in this table, you can find a different set of parameters that correspond to each calculation that they show in figure 2. So the idea here is that we are going to try to reproduce this spin polarization for this nanoconstriction here for the zigzag structure. And then we are trying to find this spin transmission probabilities. Okay, this is nice because they compare the mean field Hubbard calculations with calculations performed with siesta. So it's like killing two birds with one shot. Okay, so let's open. If you cannot hear me well, or if you cannot see my screen, please let me know.
Everything is good, no worries.
Thank you. Okay, so here is the introduction of what I just said. We are going to try to reproduce this paper here using this particular class of the Hubbard package. So let's start. Okay, here I set the common parameters that are going to be common for all the calculations that are being performed in this notebook. So we are going to use this the set D. So we are going to use the third nearest neighbors model with an orthogonal basis and the Coulomb repulsion parameter set to 2 electron volts. This is the hopping parameter between first, second, and third nearest neighbors. Okay, so I will execute this cell. So common parameters for all the systems, on-site Coulomb repulsion set to 2, and the temperature of all systems is going to be 25 millielectron volts because in our NEGF class, we performed the integration of the Green's function to obtain the density matrix using a transiesta, an energy contour that was extracted from a transiesta calculation, which was performed at a temperature of 25 millieV. So we have to use that temperature. But you can use another contour of if you want, and you can pass it to the NEGF class, and then you can use another temperature. But for this case, we're going to use this temperature. Okay, so now we have to compute the electrodes first. So we build the geometry of the unit cell here, which is going to be a zigzag graphene nanoribbon with 5. Then we build the tight binding Hamiltonian of that structure by using the parameters I just told you. So first nearest neighbors 2.7 electron volts. The hopping between second nearest neighbors is going to be 0.2, and the hopping parameter between third nearest neighbors is 0.18, following the table of the paper. This is a function that we have implemented in the Hubbard package, but you can build the dynamic Hamiltonian using CISL and setting the hopping parameters and matrix elements for the Hamiltonian manually as you want. We build this because it's handy for us, because we usually use these kind of structures and we usually have the same Hamiltonian for most of them, so it was okay for us. And of course, the dimension I didn't have here, but the dimension of the Hamiltonian by default is 2, because we want a spin polarized Hamiltonian. This is necessary for to build the Hubbard Hamiltonian object. Then we start building the Hubbard Hamiltonian for the electrodes, which are periodic structures along the x direction. So we have to pass here the number of k points in which the Hamiltonian needs to be sampled. So we only have to change the number of k points along the x direction, because that's the only periodic direction. And then we use the on-site current repulsion parameter that is defined in this cell, and the temperature of the system, which is also defined in this cell. Then we initialize the spin densities. For this structure, I added here a possible spin densities distribution to start the convergence process. You may want to use another one, but this works okay, because we know that this structure hosts localized magnetic moments at the edges of the structure, so at the edges of the zigzag ribbon, so the zigzag edges. You're going to see now the structure, but that's one atom in the unit cell. It's one atom, the first one, and then the other one. So we are placing one up electron in the bottom edge and one down electron in the upper edge. So that's the initial polarization that we are using to start the convergence process. Now we can converge, and then we have to pass. I think somebody has its mic on. I have... Thanks. Okay, so I was saying that now we can call the method converge to find the self-consistent solution for the Hamiltonian, or the mean field Hubbard Hamiltonian. So to do that, we have to pass a function that tells the code how the spin densities are going to be found, as I was telling in my talk. In this case, we can use this function, which works for periodic systems. And then we can say we are going to convert, we are going to iterate the Hamiltonian up to a desired tolerance. We want to see what happens during the convergence process. Otherwise, it doesn't print anything, but I think it's nice to see what it's doing. And then we can run. Okay, so it says that it is going to converge the Hamiltonian towards a tolerance that we set. And it found a solution in 13 iterations, so pretty fast. Then we can plot the spin polarization of the unit cell by using this function that we have in the plot class of the Hubbard package. So it takes the Hubbard Hamiltonian, and since now it's converged, the Hamiltonian is converged. Now the Hamiltonian, the Hubbard package has stored the mean field Hubbard Hamiltonian for this structure already converged. And as you can see, this is the unit cell. And I was saying before, so this spin polarization, what we did is to place an up spin here and down spin here, and then we started the calculation. But this is an initial polarization that, okay, we know for this case that it is going to work, because we know we have an intuition of where how the spin polarization of this structure is. Okay, so now we can go through the calculations regarding the scattering center, the device region. So we start by building the tight binding Hamiltonian. So in this case, we are going to do this structure here. So it's like the way I did to reproduce this structure is to repeat the zigzag graphene nanoribbon unit cell and then remove a certain atoms in the middle. Okay, so basically that's it. I took the Hamiltonian. I used this function tile from CSEL to repeat it 16 times along the periodic direction. And then I just use the function remove to remove these atoms in the middle. And then I make it finite because it's not periodic. And then I also write the geometry in the folder, which after executing this cell, you should find this file in your folder. So you can visualize it with XPRIZE or whatever you want. Then we can start with the mean Hubbard calculations for the open system. So once we have built the geometry for the device and the tight binding Hamiltonian, we can start defining the Hubbard Hamiltonian for that geometry. So we have to pass the tight binding Hamiltonian for the central region, the on-site Coulomb repulsion parameter, and the temperature of the system, which we are using the same values as we define in the first cell of the Jupyter notebook. Then we have also to initialize the spin densities. And here I am placing up spins in the lower edge, as in the case for the periodic zigzag graphene nanoribbon for the electrodes. So I'm placing up spins in the lower edge and down spins in the upper edge. So that's my initial spin polarization. So what I do here is to look for the atoms that lie at the edges, which are the atoms in the minimum and maximum Y component of the geometry. Then I define where the electrodes are localized in the device. So in this case are the first and last blocks of the geometry. So that's why I use these atomic indices. So the first atoms up to the length of the electrode, and then the same, but starting from the last one. Then we have to build the NEGF object, which will allow us to use the methods in this class that involve the calculation of the Green's function of the device, and which will allow us to obtain the spin densities from the Green's function of the device. To do that, we have to only pass the Hubbard Hamiltonian object of the device, then a list of the present electrodes that are in our system. In this case, we have two electrodes, one that grows towards the minus semi-infinite direction in the x-axis, in the first axis, and the other one grows in the opposite direction. But the Hamiltonian and the electrode is the same, so we can pass the same mean Hubbard Hamiltonian in each case. And then we say where are the electrodes mapped in the device. And then we just can call the converge function by passing, now instead of the previous function, we have to pass the specific function that tells the code that now the spin densities are going to be found from the Green's function of the device. And then the same things as before. Here, this only thing is just that we want to print the information in each step. And now we can execute this cell. So this convergence process takes a little more time than the other ones because it's it involves the inversion of a dense matrix. It's taking quite a long time. That's weird. I mean, it takes a little more time than the other ones because it has to inverse the matrix, but I don't know, let's take it so long. I'm going to rerun again everything. Oh, okay. Phew. Okay, so it found the solution in 9 iterations. And as you can see, it takes a little more time because, as I said, it has to inverse the dense matrix of the system. So it's, and in the other cases, for instance, we use the sparse matrices and the advantages of having sparse matrices. And so that's why in the other cases it's pretty fast. But still, I mean, I think in less than 1 minute, you can still find the solution for the device. Then we can plot, for instance, the spin polarization of this device that it just found. We can compare, and again, they used opposite colors for spin up and spin down than I used, but the important thing is that you see that there is a high spin polarization at the borders of the ribbon, and especially at the zigzag borders of the ribbon, and then low spin polarization in the other atoms. And that's exactly what we also get. Strong polarization at the zigzag edges and low polarization in the rest of the atoms. Okay, so now comes the part that you should try yourself. The other part is was just basically done for you. But so the idea here is to obtain the spin transport calculation for this device. So, well, I just added the cells here, but I mean, this is just copying here. I left some instruction of how one should do this. So first of all, we have to shift everything with its particular Fermi level to have everything aligned, because otherwise, if you don't do this, it will be equivalent to having some difference time applied, like a potential in the system. So that's not what we want to have, because we want to do an equilibrium calculation. So we have to shift both the electrodes and the device with the electrodes with the Fermi level that we can obtain. This is a function from CISO, of course, and with the potential that is found in the NEGF class. So let's do that. And then we have to write the inputs for the TV trans calculation. So we can go to the FDF file that I prepared. So I named the name of the device's Hamiltonian as MFH HC. this is an netcdf format. And then the electrodes, I named it like this. So we should save the Hubbard Hamiltonians with these names. Otherwise, you just can, of course, modify this input file or use an input file that you want, but this is an option. Okay, so following that, we save the mean field Hubbard Hamiltonian with that name for the electrodes with this name, according to what I wrote in the input run FDF Hamilton file. And then the same with the device region. Okay, so now we should see these two input files in etcdf format. Now, well, I just left this, but you can run this from your terminal, of course. I think it was easier to have everything in the Jupyter notebook. This is just to ensure that we don't have any previous outputs from a previous TV-trans calculation. And then we can use this, which will speed up the calculation for this case, at least, as we saw in this workshop. And then call TV-trans and save the output in this file. Really fast calculation. So now we should have everything. Yes, exactly. And then we can use CISO to extract the outputs. So in this case, since we have a spin polarized Hamiltonian, TV-trans realized that and and so what it does is two different calculations. One for the first spin index and one for the second spin index, and it will store the output in these two different files, named up and down. So we can read the output from TV-trans using CISO, and then we can plot. And we have the transmission for each spin channel. Then we can go to a reference paper and check. Okay, so we are comparing, in this case, the top panels belong to a mean field Hubbard calculation and the lower panels belong to a transiesta calculation. And this B panel belongs to spin up and this C panel belongs to spin down. So we can compare directly this blue curve to this one. So, and as you can see, I think it's pretty clear that it's very, very similar. I mean, just comparing by the eye, of course, but and the same with the down spin component here. And it's nice, this example, because you also can compare with a transiesta calculation, and as you can see, it's also very, very similar. So I think this model, if you use a correct type-binding parameterization, you can reproduce pretty much another calculation obtained with a more accurate method such as transiesta. But you can do it in 1 minute calculation and have everything in one file and obtain it locally in your machine pretty fast. So I think that's pretty handy. But of course, this is my code, so it's normal that I think like that. So I think that this is the end of this tutorial. I took much less time than other ones. I don't know if you have any questions. Doesn't look like. Okay. Okay, here I have some of them. Here, Elabeth Haidar asked, sorry, I might have missed this, but I was wondering if the U value was chosen randomly. Yeah, so this is a question that came up the other day during my talk. And the U value is not chosen randomly. It's really hard to give an explanation of how one should use should choose the U value. But I think for starters, the U value shouldn't surpass too much the value of the hopping parameters, because otherwise you should be in the strong correlation regime. So that's something to take into account. So for instance, what we usually use for our graphene-based structures is a U value that is in the range of the hopping parameters, so around 3 eV, more or less. But the U value, I mean, it will change your results quantitatively, of course, but qualitatively, you will find similar results using a U that is within a range. So what we do usually is to use these models to explain, for instance, some experiments and so on. So we try to adapt our U to try to reproduce our the experimental results. And then it's more like kind of in backwards. I mean, it's like, what is the U that you need to reproduce such experiments? I mean, it's like how to explain, so how intense are the Coulomb interaction in the system to reproduce that experimental system? More like that. And also, I mean, this U value may vary a lot for the same geometry. Even for the same geometry, if you place the geometry on one surface or another in an experiment, because the screening effect is going to be different on one surface and on another. So it's kind of hard. So it may even change for the same geometry. So thanks, guys. Dana, you answered my question also. Is that value only found in papers? You can actually, what we usually do also is to compare, maybe we do calculations with siesta, or another method, of course, with density functional theory, let's say. And then we imagine that you have a large system that you want to model with the mean Hubbard Hamiltonian. And then what you can maybe do is to model a smaller structure with siesta, maybe try to see how it compares to mean Hubbard calculation, and then use those parameters to model a larger structure, and then see what happens there. But I think that the strong point of the Hubbard Hamiltonian is kind of a toy model that allows us to play really easily with the parameters and how to see what is the role of each part of the Hamiltonian, so the kinetic part and the interaction part, to actually understand a lot of things of your systems. So I would say that that's the strong part of the Hubbard Hamiltonian. Maybe not to give a really quantitative result about that, it's more like to a qualitative understanding of the system, and I think that's really nice. It's like the accuracy you would get from a tight binding calculation. It's like, if I change this hopping parameter, then what happens to my system? Also, more or less like that. Shamik asked, in your work, you achieved magnetic nature of graphene nanoribbons? Yes, exactly. That's exactly what we do here. I mean, having localized magnetic moments, like having localized spins in your molecule, give rise to magnetic features in your structures. And actually, for instance, in one of the papers that we published, they observed a Kondo effect in two of the papers that we published. The experimentalists observed Kondo effect in two different molecules, in two graphene molecules. So that's a proof of that magnetism can be induced in graphene. So Elabeth Haidar asks, so you play around the value of U to get closer to the experimental results? Yes, exactly. We typically do that. If so, which results do you usually explore? Results of what, of experiments, or results of the U values that we explore I mean, we typically work with experimentalists that perform nice experiments, and then we try to give an explanation of how we can find such results, such experimental results with our system. So that's how we play with the U value. Yeah, and as I said, the U value that we typically use is around the value of the hopping parameter. I think you can start from that. Can Kondo be modeled by mean-field Hubbard Hamiltonian? No, the Kondo effect is a many-body effect that cannot be modeled with a mean-field Hubbard model, because the mean-field Hubbard model is actually it's an approximation, and actually it's a single particle model. So no. But you can, what we did actually is to explain why the Kondo effect was present in that molecule because of the presence of localized magnetic moments, which we could actually predict theoretically with this model. Not to demonstrate that our molecule was having the Kondo effect, but it's like why the Kondo effect is present, because there are localized magnetic moments in the molecule, and we demonstrated that with using the mean-field Hubbard Hamiltonian and also density functional calculations. Yeah, Thomas says that one can also choose a U value to come close to results from a TFT calculation. Yes, that's exactly. Yeah, you should compare to a more accurate description. Yeah. But I think what is nice of this model is that typically if you use the correct parameters, then you can typically find similar results as what you can get with density functional theory, as proven here, for instance. I think that's a strong point. Well, I think there are no more further questions. I don't know, maybe we should move to the next tutorial. Which TFT calculation would you suggest to do such comparison? On one side, you should do spin polarized calculation, because we are comparing spin polarized calculation with the mean-field Hubbard Hamiltonian. So that's one thing. And we typically use siesta, but other methods can give similar results, like VASP. I guess I haven't read by VASP myself, but yeah, I'm not sure if that's exactly your question. If not, please answer again. Ask again. Should we move to the next